Hey everyone, welcome back, and today let's solve Leetcode problem 2179 titled Count Good Triplets in an Array. So on a high level, really what the problem statement is we're given two permutations, nums1 and nums2. They're both going to have the same length n, and we want to count the number of good triplets. So a triplet, basically I, j, k, is going to be called good if 0 and n, or rather all these indices or positions I, j, and k are all between 0 and n, and the relative order of these elements at these indices in nums1 and nums2 is the same, right? So let's go ahead and look at the examples to kind of understand what that means. In the initial example, nums1 input array is 2, 0, 1, 3, and nums2 is 0, 1, 2, 3. In this case, there'd be four triplets, basically x, y, z, or a, b, c, or I, j, k, such that I is going to be less than j, which is going to be less than k, and that would be 2, 0, 1, 2, 0, 3, 2, 1, 3, and 0, 1, 3, or basically the relative order of the elements at these indices is still the same across both the input arrays. These are the four kind of triplets that meet that property. But out of all these four triplets, there's only one triplet that actually satisfies the position 2 at x, position 2 at y, and position 2 at z kind of property, where again the relative order of the elements is equal, or rather is same, right? And in that case, that would be 0, 1, 3, right? 0, 1, 3, right? And so that's going to be the only triplet in across both the arrays that are actually considered to be good. In example 2, we have our input array nums to be 4, 0, 1, 3, 2, and 4, 1, 2, 0, 4, 1, 0, 2, 3. And in this case, we actually have four good triplets. And those four good triplets would be 4, 0, 3. They would be 4, 0, 2. They would be 4, 1, 3. And there would be 4, 1, 2. And those would all be considered good triplets, where again the three distinct values are in increasing order by position in both the input arrays, right? So for the constraints here, we see that the length of our input array nums and nums 1 and 2 are both going to be equal to n, where that value is between 3 and 10 to the 5th power, and any value in those input arrays are going to be between 0 and n minus 1, where they're both permutations from 0 to 1, 2, and minus 1. So what are some key observations that we can really make in this problem to solve it in the most efficient way possible? Well, let's go back to what the constraints really told us. We're given that both of these input arrays, they're basically different permutations, right? They're permutations both having the same length of 0 to n minus 1. And so they're going to contain the same values from 0 to n minus 1. The only thing is they're going to contain those values in a different order, because again, that's really just the definition of a permutation of a set. It's going to have the same exact values, just in a different distribution, or the elements are going to be in a different order. So again, let's kind of go back and recall, what do we actually want for a triplet to be good? Well, the relative order in nums1 has to match the relative order in nums2 for any triplet values or indices I, j, and k, right? So we need to kind of keep track of the position of all the different elements across both input arrays, right? Position information is vital in the problem. So how can we kind of scale that up to something that we can really observe and lead to make a more, rather comprehensive solution? Well, we can basically just map each value in nums2 to its index and then convert nums1 into the array of indices from nums2. And then if we do that, once we actually build that hash map, the problem is as simple as we want to count the number of increasing triplets in the new array of indices, right? Because we've transformed the problem into a simple count the increasing triplets problem by mapping those values to their index in the second input array, and then just converting the original input array into the array of indices from the second input array, right? Where we simply just count the number of increasing triplets in that new array of indices, right? So how are we going to solve this problem? Really, it's just a high-level rundown. We're going to have an index hash map, if you will. I'll just call it index in nums2, to kind of make it easy to decode. Basically, it's going to be a hash map, or hash map to basically map every single value to its corresponding index in nums2. And we're also going to have a binary indexed tree. This is also something called the Fenwick tree. Basically, it's going to be used to efficiently count the elements that are less than or greater to that kind of current element in that logarithmic time. Again, logarithmic time is very efficient. We want to have the most efficient runtime, and big O of log n is a very efficient runtime. So let's go ahead and get into the code here. So for that Fenwick tree, kind of binary tree, not binary tree, but Fenwick tree, index tree, I should say, implementation, we're going to have a separate class for it. So I'll just call it BIT, class BIT binary tree. Basically, it's going to be short for binary index tree. And again, binary index tree is simply just a structure where it basically allows us to query prefix sums and update those elements in those sums in big O of log n time. Again, log n is simply nothing but logarithmic time, which is, again, very efficient if you recall in runtime complexities. So for every class, of course, we're going to have our standard init function here. Oops. Right, and for my kind of parameters in the init function, of course, I'm going to pass in self. Always want that self, and also a size. Now, the size input array is basically going to have, going to be used to initialize the tree. So I'm just going to call it self.tree, and it's going to be initialized to all zeros, and it's going to have a size of size plus 2, right? And the whole point of this kind of tree is, again, the init function is basically the constructor for any object for this class BIT, right? And in this constructor, we're always going to initialize the binary index tree, or the BIT. The BIT is going to have a size of size plus 2 zeros, or size is really just our input parameter, if you will, right? And why are we adding plus 2? Why are we adding those 2 extra zeros? Well, because we want to always add the extra space to prevent the index issues for one-based indexing, because of course we don't want to get an index out of bounds error in our solution. I mean, that's just really annoying. Now, in this class, we're also going to have an updating function here, so I'll call it def update. And for our updating function, we're going to have 3 different parameters if you include self. So of course, we're going to have self. We're going to have I, which is again just the current index I, and we're also going to have the current value, which I'll just call val. And in this updating method or function here, we'll increment our pointer index I by 1, and while this pointer I is still in bounds. How do we check if it's in bounds? Well, if it's still less than the length or the number of elements we have in the current tree, so self.tree, well, then we want to get self.tree at the current index I, and we want to then increment it by the current value. And once we increment it by the current value at that index, we want to then actually update our value, update our index. Is going to be I, and it's going to be, can't find, there it is, I ended by negative I. Right, so what are we really doing here with this kind of bitwise operation, if you will? Basically here, we're updating, this is the main update method for every index and value, right? We're adding the value to the position I or index I in the tree, and really here, all this is really doing here, we're incrementing I by I and by negative I, basically removing to the next responsible node in the BIT from the current pointer or index I, right? So now let's actually get to the query function here. Right, and for this query function here, apart from self, all we're going to have is one pointer or index I as our parameter here. And the first thing that we're going to do still is, of course, increment I by 1, and then initialize a res to be 0. Right, so while I now is still greater than 0, right, while it's actually non-negative, that is, right, it's still going from index index 0, we're going to increment to res, so res plus equals self.tree at the current index I, basically incrementing its value in the current result, and then decrementing by I ended by negative I. There it is. I always have trouble finding that key. So we're decrementing from I ended by negative I, and effectively returning the result, whatever it may be, right? So here, again, this is the main query method or query function in this BIT class, where we're returning the prefix sum from 0, or rather index 0, to I in the tree, right? And we're basically adding up all the relevant values while moving up the tree across those indices. So that's actually it for the BIT class here. Now let's move on to the main class, and more importantly, the main function here, right? And the goodTriplets class solution that Leetcode actually provides to you, right? So the first thing that we're going to do, like we usually do for most array problems, is grab the length of our input array nums1, right? And technically nums2 as well, but really we only need nums1, right? So we'll get nums1. I think it's only num1. I don't remember for sure. No, it's nums1. Okay. Yeah, so we're just basically grabbing the length of the array for n, basically the n value, right? Because of course it's just easier for us to iterate over and build across both arrays. It's just a lot quicker instead of having to type length of nums1 or the length of nums2 each time, which can get annoying, right? So now let's actually get that hash map. Again, this is the main observation that we made a few minutes ago of the hash map mapping each value to its index in the second input array. So I'm just going to call it position. I said I was going to call it index to nums. Doesn't really matter. I'll just call it position. Basically, we're mapping every single value in the second input array to its index. And I'm going to use something called, in fact, I'll just do IDX. And I'm going to use something called dictionary comprehension here. Basically, every single value is going to be mapped to its index for every single index and value. And what's a very simple way to map every single index and value as we iterate over an iterable using the enumerate function in Python, of course. So in the enumerate of nums2, right? Basically, for every single value in the input array nums2, we're mapping it to its corresponding index in the position hash map using that enumerate method, because again, the whole point of enumerate is to kind of correspond and get every single index with every single element as we iterate over a list or any other data structure like that, right? Again, kind of putting us back to our initial main observation, where since both arrays are actually permutations of each other, we know we can always map each value to its index in nums2, because then that dictionary is going to help us quickly look up where a value actually appears in nums2, more specifically which index it appears when we're trying to actually consider it in the correct triplet. So now let's actually get transformed. And the whole point of this transform method basically is going to be every single position, at the value for every single value in the input array nums1, right? So very straightforwardly here, basically for every single value in nums1, it's going to be basically its value or index in nums2, and they're all going to be stored in transformed. This is the main kind of like part of our pre-processing, if you will, of our code here. All right, basically, it's going to be each value from nums1 being replaced by its index in nums2, which gives us that sequence of positions that kind of depend on each other for both input arrays, because now we really just want to count the increasing triplets in this new list. We've completely transformed this problem into how many increasing triplets are there in this new list across the indices of equal values in nums1 and nums2, right? So now once we've actually kind of built that transformed array, now we want to actually begin the prefix information counting, if you will. And the way we're going to do that is actually first initialize left. It's going to be all zeros, sorry, and it's going to have a length of course, n, and we're also going to get bit 1, and it's going to be an object of the bit class. So I'm going to say bit, and of course, since we have exactly one parameter, of course I'm going to pass in the length of our input array nums1 and nums2, n, right? So we're basically initializing left again. It's going to be left, the whole point of it is going to be left at index I is going to store how many numbers are less than transformed at index I to its left, of course. And bit 1 is basically a binary tree indexed tree to keep track of what we've seen so far across the input array nums1. Right, so now once we've actually initialized that, well, now let's actually start iterating through all n elements, or basically just n times. So for I in the range of n, right, so in each iteration in this, right, we'll get left at I and increment it accordingly. So left at I is not going to be incremented to be bit1.query, and I'll just quickly type this out and kind of explain how this works. So here, again, keep in mind bit1 is nothing but the object of our class here, transformed at I, but the key thing is we're going to -1 here. And very similarly, we're going to get bit1, but call this time the updating method, and we're going to pass in transformed at I, and then we're going to kind of put a comma there and then -1. I think I might have messed up the syntax here. I hope not. Yeah, should be right for our second parameter. So what are we really doing here? Well, basically in the range of n, basically for each index I, n times, of course, because we have n i's or n indices, we're using the tree to query how many numbers that are smaller than transformed of I, how many numbers that are smaller than transformed of I, how many of them have actually already been seen, how many of them have we already iterated over or seen before, right? And that's why, of course, we're getting our bit1 object, and then using .query to call the query method, passing in transformed at I -1, All right, once we actually get the number of numbers smaller than transform divide that we've already seen for every index, we're basically then just going to update the tree to include the data from transformed at index I. Again, this is kind of the main prefix information idea, right? How many values before index I are smaller than the current value to accurately get the number of increasing triplets, which is, of course, what the problem wants, right? So once we've done that, well, guess what? We've now completed the prefix, not pre-processing, but the prefix information. Guess what? Now we have to then complete the suffix information. And so the way we're going to do that is we're going to initialize right. It's going to be, of course, very similar structure, all zeros with a length of n, and we'll get bit 2 in this case, and it's going to be still an object of bit, passing in n. It's really just for the second input array, or rather, for the second bit count, if you will, or the second bit object, right? And again, to get the suffix information is basically how many numbers greater than the current number are to the right of it, right? So once we actually get that, now let's actually begin the pre-processing, but at this time we're going to be going backwards because, of course, we're going from the right, or rather, how many elements are greater than to its right. And so to go backwards in Python, or rather iterate backwards in Python, we're going to have 3 parameters. So it's going to be in the range. Starting from the largest value, which is n minus 1, we're going to go up until -1 exclusive, or 0 inclusive, and we're going to decrement by 1 each time, or in each index, to go kind of to the left, to go backwards, if you will, but losing 1 each time. All right, you can think of it as a reverse loop, if you will. And very, very similar structure to lines 24 and 25, and the prefix computation, or prefix counts. Basically, we're going to get right at index I, right? Still the query method here. It's going to be bit2.query, basically calling the query method for the current class. We're going to pass in n minus 1, and we're going to subtract this value, not equal to, but we're going to subtract this value, so bit2 soul.query, but in this case, we're going to pass in transformed at index I, right? And really, I'll explain this in a bit. We'll also get update and update that accordingly, so bit2.update. And for our parameter, of course, you guessed it, it's still going to be transformed at the current index I, and we're going to pass in a 1. So again, what are we really doing here for the reverse loop suffix information, or suffix counts here? Basically, in the reverse loops, so still for each index I, we're querying how many numbers are greater than the current transformed index at index I, how many of them are already in the tree, i.e. to the right of it, right, that we've already seen as we iterated over them. And once we actually get the count of those number of values, we'll then update the tree with the current value. Again, that's going to be the suffix information. We've got the prefix information, now we've got the suffix information. Now we can combine the counts to get the total accurate number of increasing strictly triplets across all indices or elements in both input arrays, right? That's going to be the final step to actually combine those counts across in our tree that we actually built. So again, now I'll initialize a final resulting list, or rather resulting integer, 0. This is effectively what we're going to be outputting, right? And the whole point of this result is to store the number of good triplets, i.e. the number of increasing triplets, or in increasing order triplets. And the way we can do that really simply is just to combine the counts literally in the left and right prefix and suffix respectively arrays. So for I in the range of n, still for each index or for all the elements that we have, we're adding to our result left at this current index I, or element or index I, and right at this current index I. But the key thing is, this isn't adding, this is actually multiplying, because we want to get the accurate number or count of valid triplets. Where again, the total number of good triplets is going to be calculated for each index I. Basically, the number of valid triplets that have I as the middle element, where again I is basically the index or element that we're iterating over, basically it's going to be left at I times right at I. Again, that's the number of valid triplets that have I as the middle element. Why in the world is that the case? Well, because we need one number that's less than transformed at I to be before it, and we need one number that's greater than transformed at I after it. And so the total number of different permutations or possible choices we have for I to be the middle element, using all the different elements that we have as choices, is going to be left at I times right at I. The number of elements that are less than it that go before it times the number of choices, or the number of different elements we have that are greater than it that go after it. And effectively, once we actually compute that value and increment our res integer accordingly, of course, we then want to return res, because that's going to store the total count of good triplets that we computed on lines 32 and 33 in that processing for loop. So unless I made in syntax 00, this should be accepted, and there should be a valid solution. Okay, let's go ahead and see what I did wrong here. left at I. Okay, it says bit has no object, which is quite weird. Don't exactly know why that is. Maybe a query. Did I spell it wrong? So I'm not exactly sure why it isn't registering. I might just kind of share you guys my final code that was actually accepted at the end of this video if I don't actually get to decode it in the middle of the video. Sorry about that, guys. That's kind of been something that I kind of just have to get over with, if you will. Not really a better way to do it, but before we kind of just get lost on this, let's go ahead and explain what this code does overall and the memory complexities. So on a high level, how are we really solving this problem? Well, basically we're transforming the original array into a sequence of positions in the second array, and then we actually use that BIT or binary indexed trees or Fenwick tree to actually efficiently compute how many values before and how many values after each element are smaller than or greater than respectively to get the accurate element of the number of increasing triplets for each index I as the middle element. Finally, we're multiplying the counts to actually get the total number of good triplets, where the triplets are basically preserving the order across both arrays. Right? So for the runtime complexity here, it's going to have a runtime complexity of big O of n log n. Why? Because to actually build the maps, that's linear, of course, big O of n, we're going to have two different bit passes. Those are going to be fully simplified big O of n log n. And the final pass is, of course, big O of n to actually build or get the number total of counts. And so overall, the bottleneck or fully simplified runtime complexity is big O of n times log n or big O of n log n. So for the memory or space complexity, it's actually just going to be very straightforwardly a linear memory complexity or space complexity big O of n. Why? Because the bits themselves take big O of n, and the arrays and mappings like we see for position and transformed and left and right, if you will, they're going to be big O of n. And so really, this is just a linear big O of n space or memory complexity. Right? So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.